Guys, I'm here at Legacy EV booth at Barrett-Jackson, and with me is Eddie.
Yep.
Eddie, can you please introduce yourself quickly?
So my name is Eddie Borisevich. I own and operate a company called Revel Systems out of Southern California. We designed these drive systems for classic vehicles. We basically repurpose Tesla motors, reconfigure them, put different gearboxes on it, and add a bunch of billet to them to make them look very hot rod-esque.
Well, there's a lot of classic metal here in the booth at Legacy EV. Cadillacs, we got Land Rovers. Is it fair to say, are you one of the electric hot rodders? Is that fair?
I think that was very fair to say. We're doing exactly what the hot rodders did 50 years ago. I mean, it's textbook. You take a motor out of a big sedan, a lot of horsepower, you put it in something smaller, and you hop it up.
Yeah.
So we're actually pushing these motors more than Tesla would have pushed them. We're souping them up. We're putting them in different applications. We did a streamliner last year at Bonneville. So this is exactly what hot rodding is about.
Okay, I want to get to Bonneville a little bit later.
Sure.
You have a chassis here that kind of demonstrates what we're talking about.
Sure.
So what kind of a chassis is this? Like a Mustang could be on the same platform?
So yeah, this actual chassis came out of my 1965 Mustang.
Okay.
Mustangs don't have chassis, they're unibodies. The Roadster shop actually built this chassis for us. We've been using this chassis on that. The reason we went with them is because now I can update the car, make it handle well. Plus we're pushing a lot of torque through this particular car on the unibody, so there's a lot of twisting,
right.
And we want to make sure that that was all gone. So we went with the Roadster shop, love their chassis. It's very easy to integrate with our systems. We're smaller than a V8 with the transmission, so the package is much shorter and tinier. We'll be able to tuck everything back inside this chassis with a very
I mean, normally the V8 engine would be here, right?
Yeah, it actually sticks out to almost here.
Yeah, in front of the front axle.
Correct,
right.
correct. If you look down, you can see where the old engine mounts were for the 289.
Down here?
Yep.
Yeah.
So that's where the middle of the V8 would have been. My firewall in this car sits right about here.
Okay.
And then all the motor and everything else sits underneath it. You got a low center of gravity. Also, what you did is you pulled some of that weight back into the middle, towards the middle of the car.
Yeah.
One of the neat things we did with this car too is we were able to plan where we're going to put the batteries to balance it out. So as this car sits on scales right now, is a perfect 50-50 split, which is very difficult to do to a car back then.
Or a classic, any classic car, right?
Any classic car, because you have that giant, cast iron V8 up front, a lot of weight just kind of planted over the front of it. So we wanted to update it. No more bump steer because of the chassis. We have rack and pinion steering in this vehicle. We have power brakes, power steering. It's basically fully updated. And you've got this beautiful old shell and an iconic car that's been around for 60 some years.
Yeah, totally. So let's dig in. Can we go through some of the components?
Absolutely.
So you said you started, or you're using some of the Tesla motors?
Yeah.
Or kind of tell me what you started with and how you're hopping it up, I guess.
Okay, so what we did is we took a Model S motor out of a Tesla, which is actually this part right here.
Okay.
Teslas are by nature transaxle. So what we do is we take their motors and we shave them down just to the core of the motor. As you can see some of these markings here from our machining, that's where the transaxle used to come out.
Okay.
We remove the original gearboxes, we remove the pumps, all that stuff. So it's just the bare motor. We park it longitudinally. We make adapter plates to go the torque trends torque box.
Yeah.
And what that does is give us a gear reduction. We don't have a transmission. That's the torque box. Yeah. So that's basically like a 1.9 to 1 reduction.
Okay.
So it takes our high RPM, reduces it down, and also what it does is it's a torque multiplier. So we're taking about 400 to 500 foot-pounds of torque that's coming out of the motor and multiplying that by a factor of 2, so we get about 1,000 foot-pounds of torque coming out of the yoke. And that's at 1 RPM. People look at me like I'm crazy when I say that, but that's...
I am looking at you crazy. Okay.
But that's what it's doing.
Okay. So then what's this up here?
Okay, so that's what we call our main mount. It actually serves a lot of different functions.
Yeah.
It cools the electronics, so we have a passage that comes in here. It takes the coolant, it passes it through the inverter.
Okay.
The inverter sits in this round area up here where we call the revolver.
Okay.
Cools the inverter. Also, the fluid gets channeled into a water jacket that cools the motor, and also the rotor inside gets cooled as well. So there's 3 major components that get cooled through this block. So we have basically a block in here with a manifold. It channels all the fluid where it needs to go. We have an outlet back here, an outlet over here, and an outlet underneath it. So 1 channel in, 3 channels out. We could control flow rates and everything else to cool certain items. We've increased the cooling capacity of the particular motor because the amount of fluid that it's going through it now is more than Tesla used to do. And the way we ported our channels is we could cool the inverter separately from the motor, and we have a little bit more flexibility on how we do that.
So you want to keep the motor as cool as possible. Is that fair to say?
That is very fair to say. When we do racing or racing applications, we actually chill these motors down below ambient as far as we can. I've actually brought them down to freezing levels, 0 degrees C. So we get that much more time out of our runs. Unlike a combustion,
you're talking like drag racing or circuit racing, or
we did Bonneville.
Bonneville. You going for high speed?
Yeah, and Bonneville I think was one of the hardest things we ever did because of how long you have to sustain that kind of horsepower. Quarter-mile drag race, and I'm not knocking, I love drag racing, but you're doing a quarter mile. We're doing 5 miles wide open, and it is just brutal on everything inside.
Batteries, motors,
all of it.
Right.
Just, you get so much heat buildup because you're pushing so much power through these things. So that you do have to cool them. And pre-chilling is nice. Unlike a combustion engine, we don't need to get up to temperature. We want to stay as low as possible.
Good. So now, is this carbon fiber?
Yes, it is.
So you have a carbon fiber drive shaft. Why'd you go with this orientation?
Okay, so when we first built this car, we wanted to put some of the batteries in the floorboard of the vehicle. What that did is we had some space issues, so our tunnel's very narrow. We talked to Mark Williams and a couple other driveline manufacturers and said, look, with that diameter, the only thing you'll be able to do with that kind of torque is to go carbon. So we said, sure, we didn't want to break anything. We have a scattered shield in the back for the U-joint, also a scatter shield that is part of the tunnel. So if something does break, it doesn't come up and say hello to us. Safety is a big thing for us. We do have batteries in here that could cause problems if they short out. So we want to keep all the danger zones down to a minimal. So the carbon driveline was like the ultimate choice for what we're trying to do here.
And you're talking about 1,000 pound-feet of torque, possibly. So you have to handle a lot of torque.
Yes, and carbon does that very well.
And
carbon's a magic thing. I love it.
It's also lightweight. Right?
Very lightweight. My 6-year-old kid could pick this driveline up in one hand. And it's pretty interesting because the one that fell out of this car when I tore it apart was very heavy.
And the rear axle, I mean, you can do whatever you want, but you need a stout rear end. Right?
So what we did here is we did a 35 spline on the axles. It's a strange rear end with a true track posi. It's a Ford 9-inch aluminum housing. We ran the numbers on it and made sure that this was going to be able to handle the amount of torque that we're throwing at it. So far I had 0 problems with it. We've probably got over 100 launches in this car. We were testing the motor pretty seriously and didn't break anything at all. So we're pretty happy with the outcome. Once again, if people are going to be installing these high torque motors in their vehicles, you can't just run your standard differential. You're going to break the teeth out of it. A lot of things are going to go wrong. We don't even recommend using an open differential because the spider gears are just going to get hammered on.
I gotcha. So we talked about batteries briefly, but what I'm learning about talking to a lot of engineers of electric vehicles is that the motors can put out more power if you can feed it the electricity, right? So where is the battery technology, or which technology did you go with on the batteries?
Well, we're using lithium type batteries for this.
I mean, that's what it's available right now.
That's what's available. I mean, there are other things coming out. I don't think there's going to be a giant, oh my gosh, we found the Holy Grail. I hope I'm wrong, but it is, it's a step-by-step situation. Things get better and better. In the last 5 years, batteries have improved quite a bit. I think they've doubled in capacity. They're getting smaller, less resistance inside of them, so you get less heat buildup. And we know more about them. They're more available to us. When we first started doing EV conversions, you could not go out and buy a brand new battery. You'd have to go to the junkyard,
to repurpose something, right?
Exactly. Pull a Nissan Leaf down or Chevy Volt, and we're ripping things out of cars and then we're repurposing them, which is it's a little dangerous because you don't know where that battery really came from, what quality it was in. Now we're seeing a lot of the third-party manufacturers produce cells that now we could use and configure in a purpose that we could build these high horsepower motors with. Like for Bonneville, we had to build a custom battery pack for that car. there was no battery that could sustain that kind of power output.
Well, you also have a streamlined application, right? So tell me about that car a little bit more. So what kind of power and what kind of batteries, how'd you do it?
So basically we ran 2 of these motors inside that car.
Okay.
The first time we went out, we used a Model S P100D battery pack. It just couldn't get us over 300 miles an hour. It didn't have enough energy dump capacity to get us the amperage we needed to sustain that kind of power. So what we did is we went back, we found some prismatic cells out of, I believe they were out of a Honda Insight.
Okay.
And then I sat there and I tested these batteries. I shorted them out, I cooked them, and we tried everything we could to destroy them and saw whether they were happy and angry. When you're racing, you're not going by the manufacturer's specifications.
Well, you're pushing the limits.
You're pushing limits
Yeah.
because it's racing. But we did not want to have a situation that we were going to injure anybody or catch on fire. Race cars catch on fire all the time. EVs catch on fire. Everyone knows about it. And the last thing I want to do is go out there and make the whole industry look bad. So we developed our own battery pack out of these cells I found, stitched it all together, 1,152 of them. Took us 3 weeks of tedious hand placement, wrapping, friends were over, everyone was helping out. So we were able to design a battery pack that sustained 3,000 amps continuously.
Wow.
Yep.
What would the standard battery be?
Like these types of motors could do between 1,200 and 1,500 amps, but you're only doing that for short bursts.
Okay.
When's the last time you got in a car and held it wide open for 5 miles?
Well, we do some towing tests
that's different.
and pulling up a grade with a heavy trailer. So that's my only other comparison.
So you're pushing stuff, but most people aren't going to be doing that kind of driving. So when like the Teslas and the Nissans and all these electric cars, they're not designed to be wide open for that amount of time. So we had to run a different cooling system, different battery systems, because the burst is fine, but we're doing a continuous pass, which is extremely taxing on this stuff.
I gotcha. And what was your final result? Your speed at Bonneville?
We did 353.8. So we not only beat the national record, but our national time right now beat the fastest international time. So we do have the great honor to say that we have the fastest electric car on the planet.
There you go. We're not talking about airplanes, Rolls-Royce, okay?
Yeah.
We're not talking about airplanes, cars.
Cars. Fastest electric car
that are on the ground.
Yep.
Yes. Well, that's very impressive. So you sell some of these kits? I mean,
yes.
Use it, through Legacy EV and stuff like that?
Correct. So we basically design and manufacture this motor system. It comes with basically everything you need except for batteries. Batteries not included. I know that kind of sounds funny, but it's batteries not included. So that's basically the motor, the inverter, the computer systems, electronics, full wiring harnesses, down to the throttle pedal. We provide all that. You provide 12 volt and the 400 volt, you got yourself a race car.
There you go. And you can put it in anything. I mean, truck, four-wheel drive, whatever. Whatever floats your boat.
Absolutely. Yeah. We've put it into streamliners. This is a 65 Mustang. We have a couple other Mustang builds that I don't know how it happened, but our customers have Mustangs. Okay. So we got a couple more.
It's a popular car.
It's a popular car. But it's just weird that all of them are Mustangs. And then we're building a C10 truck as well for one of the guys back at the shop. And it's more of a drag car for showing off and seeing what the actual power plant could do.
I gotcha. So have you also seen, have you done a lot of any manual transmissions backing this up?
Some people have done electric motors with manual transmissions. Personally, I don't like to do that. Transmissions were designed to keep engines at a certain RPM where they're producing the most amount of efficiency. Electric motors don't work that way. We produce max amount of torque at 1 RPM all the way through our spectrum of RPM. So by putting a transmission behind it, you have more mechanical losses and you're basically just wasting power.
Yeah.
Some people are like, well, I like to shift.
Oh, yeah. Okay. Well, you can.
You can. We don't recommend that.
Okay.
And you're going to have to build a pretty beefy transmission to hold that kind of power. And to me, you're just adding more complexity. The whole point behind this thing is simplicity. We have very little moving parts in this thing. The more moving parts you want to add is the more failure points you're going to have to break things. So sure, you want to shift, go shift. We went 0 to 353 miles an hour in first gear.
With no extra gearing.
No gearing. Yeah. That's what we did at Bonneville. This car, I've had this thing, wheel speed up to 140, 150 miles an hour without shifting.
Yeah.
So It's more efficient.
Are all motors similar quality? Can you tell me a little bit about, what's like the cream of the crop, I guess?
Well, there's a lot of technology out these days. These are actually induction motors, so this is actually an older technology. The new Tesla stuff is basically called synchronous reluctance. So basically what they do is they have some permanent magnets in there. It's kind of a hybrid between a permanent magnet and an induction motor. There's axial flux motors. There's a lot of different types of motors. Those old brushed DC motors we had as kids.
Right.
Those are very inefficient. So the efficiency of this motor is like 94%.
That's really high.
Yeah, very high.
Yeah.
The newer Tesla stuff I heard is closer to 98, 97. I mean, you're splitting hairs here, but if you're talking about a car that does 200, 300, 400, 500 miles, an extra 20 or 30 miles is a big deal.
Yeah.
We don't really care because we're racing. I personally like induction motors myself because they aren't prone to break down magnetism due to heat. So for race applications and heavy use applications, I'm perfectly fine using inductions. Some people are like, well, that's not the cream of the crop. Well, I'm not trying to become the most efficient person down the street. I'm going to try to produce the most amount of power. And these do that very well.
And also dependably do it.
It's very dependable.
Reliably, right?
And we don't have to use rare earth materials for these types of motors. This is an induction motor. It's comprised basically of copper and a ferrous material like steel. So there's a lot of that type of stuff in there, aluminum obviously. So we don't be using neodymium or any, there's not a single magnet inside this motor. It makes its own energy by basically inducing the rotor.
And you mentioned 92% efficient, 98% efficient. Those are insane numbers because normal combustion motor, the best ones we have right now for gasoline are like 40% efficient,
correct,
right?
Yeah.
And we're talking about taking the fuel, converting it to work actually, right?
Yep. And then you got
heat losses, friction losses, all that
exactly.
stuff. So talk about over 90% efficiency. I mean, it's blowing my mind.
Correct.
Just thinking about it. So
yeah, and that's kind of the way of the future. And we didn't do this because, and people are going to probably hit me for this pretty hard, but I'm not doing this to go green or anything like that. That's a kind of an offshoot of it. We're doing this because it's just the power behind it is massive. And I love my gas cars. I drive a diesel 6-liter, a big Garrett turbo in it. I got the thing turned up. I offset my carbon footprint somehow.
Okay.
But getting in one of these is the torque of a diesel, and the efficiency is out the roof, and it's instantaneous, and it's just as fun, actually more fun to drive than my big diesel that has all that other fun stuff.
Yeah.
So that's why I do it, and that's what I think a lot of the hot rod guys, they get a little skittish. They're like, well, it's electric. I don't want to do electric. I'm like, but just think about it from a power perspective. Forget about all the green stuff and all the politics behind it.
And all the tire melting you can do.
Exactly.
Yeah,
it's more fun.
Right.
So it's like basically I'm a big kid now, and I built my RC car and I get to go drive it around.
Awesome. Well, thank you for spending the time.
My pleasure.
I appreciate it.